Are you here for the 124?
Yeah.
Okay. Okay. All right. Hi everyone. So today today's the final exam review. So we're just gonna go through these problems. It's pretty long. It's like 2 hours. So yeah, let's just like marathon through some of the problems. So problem one is true or false. So let's go through each of the parts. So part A says if x is a pseudoprime, then x is also if x is a 2 pseudoprime, then x is also a 4 pseudoprime. So what does it mean for something to be pseudoprime? So a number x is a 2 pseudoprime if it is true that 2 to the x minus 1 is congruent to 1 mod x, but x is not prime. Okay? So that's just the definition of what a pseudoprime is. And the reason we use this, this is part of Fermat's test, right, for primality. And Fermat's test, is a way that we can say, if a number is prime, it'll always pass Fermat's test. Like Fermat's test will tell you, if your number is actually prime, then 2 to your prime minus 1 is always going to be congruent to 1 mod your prime. However, it is possible for numbers to be composite, yet 2 to the x minus 1 is still congruent to 1 mod x. So this is what it means for something to be a 2 pseudoprime. Yeah?
When you say 2 to the x equals 1 mod x, you mean 2 to the x minus 1 mod x equals 1? Or?
Yeah. So this whole thing is taken mod x. So it's saying like this is an equivalence between these two things, but it's taken mod x. Okay. So like this, the remainder of this number, when you divide by x, is equal to 1. Okay. So now the true-false question is saying if something's a 2 pseudoprime, then does that imply something's a 4 pseudoprime? So a 4 pseudoprime would mean that 4 to the x minus 1 is congruent to 1. This is all taken mod x, right? And so of course this implies this, because 2 to the x minus 1, what if I just took both sides and squared it, right? If I took both sides and squared it, it would give me exactly 4 to the x minus 1 on the left-hand side, and 1 squared is 1 on the right-hand side, so this statement is true. Okay? So let's move on. Part B says, so there's been a little correction in part B. So the new problem should say, suppose let x be an integer, and suppose I can write x minus 1 as 2 to the t times u, right, where u is odd. Okay, so that just means that x minus 1, like, 2 to the something means all the even powers of x minus 1 are here, and u is an odd number. And the statement says, suppose then I find a number, some integer a, such that a to the 2 to the I times u is congruent to 1 mod x, but a to the 2 to the I plus 1 times u is not congruent to 1 or minus 1 mod x. Then the statement says true or false, x is composite. Okay. So you might recall the format of this, right? This is from something called the Rabin-Miller test, right? And the Rabin-Miller test was our way of improving upon Fermat's test. So this one was Fermat's test, right? And this one is Rabin-Miller test. Rabin-Miller test was our way to improve upon Fermat's test, because in the Fermat's test, we had these things called the Carmichael numbers, right? The Carmichael numbers were special like composite numbers, such that it didn't matter what base I chose, 2 pseudoprime, 3 pseudoprime, 5 pseudoprime, etc. It would always fail Fermat's test, right? And so we moved on to something called the Rabin-Miller test, because in the Rabin-Miller test, there doesn't exist these numbers, these Carmichael numbers that make us fail every single time. So in the Rabin-Miller test, if your number x is actually composite, well, eventually, if you try enough different a's, like you'll eventually find it. Find a particular a that will be the witness to your number being composite. Okay. So now the question is true or false. Is this the statement of the Rabin-Miller test? And the answer is false. This is actually the backwards direction. It's not the right direction, I guess. Okay. So in the Rabin-Miller test, what you're supposed to do is say, if I can find a number a such that a to the 2 to the sum I times u is congruent to 1 mod x, if this is the actual Rabin-Miller test with 2 to the I, a to the 2 to the I minus 1 u is not congruent to 1 or negative 1. Recall, like, the logic behind the Rabin-Miller test was if mod x, like if x is prime, there should not exist any like non-trivial square roots, right? You see how this number up here is this down here is the square root of 1, right? Like thing squared would be equal to that, right? Because if I square it, I'm just multiplying the exponent by 2, right? And so 2 times that would give you 2 to the I, right? 2 times 2 to the I minus 1 is 2 to the I, right? And so this thing squared should give you this, right? So if this happens to be something like, congruent to, I don't know, like 3, right? And is not equal to 1 or negative 1, then it tells you that x is not prime, because only composite, only when you're looking at mod composite numbers can 1 have like a non-trivial square root. Can there be some number whose square is 1, but that number not be minus 1 or 1? Yes?
So that step from, you know how you're saying 2 to the I minus 1 squared gives you 2 to the I?
Yes.
So does that, like from the step up top to the next step, is that like the step in the recursion where if the result of modding a to the 2iu equals 1, you repeat with like x to the 1/2 or whatever?
I'm not really sure what you mean by recursions. Like,
so like you mentioned that like the key distinction is that it's 2 to the I minus 1 and not plus 1. So like
yeah,
what?
The distinction is like the test says, if you have some number a that is like congruent. So like if you can find some number a, like I guess the test says if you can find some number b such that b squared is congruent to 1 mod x, but b is not congruent to like negative 1 or 1 mod x, then like this tells you like x is composite. That's what the test says. The test says, look at like if any number when you square it, it gives you 1 mod x, but the number itself is not 1 or negative 1, then that tells you that x is prime. And like a simple example is 8, for example, is not prime, right? 3 squared is congruent to 1 mod 8, right? 3 squared is 9, which is congruent to 1 mod 8. Yet, but 8 is not prime, right? But if you looked at something like mod 7, for example, you wouldn't be able to find me a number whose square is 1 mod 7 that's not 1 or negative 1. Does that make sense? I guess. Yeah. Okay. All right. So let's move on. So this test is just false because it's written in the wrong direction. So part C says when using both the union by rank and path compression heuristics, each find operation takes O of log star n time. Okay. So this is a tricky one because you remember from class, we did this whole extensive proof about, log star, right? And so it seems like, yeah, the result that we got was that, doing the find operation takes O of log star n time. But there was a little catch, right? It wasn't that every operation would take O of log star n time. It was that amortized, as in aggregated over a bunch of operations, on average, each operation takes no more than log star n time, right? So that's why the statement is false. It's not true that every query will take log star n time. It's that on average, if I run, n queries, then on average, each one will take no longer than log star n time.
So the worst case should be log n, right?
The worst case is log n, that's correct. And you can give an example where you get achieve log n, right? Like if I just build up, a tree with as many nodes as possible, right? A tree of height k has at least 2 to the k nodes, right? And so you can build up a tree that has height log n, and if you call find on the bottom node, that will take log n time, right? And so it's impossible. It's possible that a single query will take more than log star n time. But you see, like once you call find on that bottom node, that long path of length log n is now gone, right? And so that's the intuition as to why like future calls will not take as much time. Okay. Part D says Kruskal's algorithm is better for dense graphs, while Prim's algorithm is better for sparse graphs. So this one again is false because it's kind of just the wrong direction again. So let's recall what's the runtime of Kruskal's and what's the runtime of Prim's. So recall these are both algorithms for finding minimum spanning trees, right? And the intuition behind Prim's was that I'm going to start with one node, right? And I'm going to start growing a spanning tree from that node, right? And so the way we looked at Prim's was very similar to that of Dijkstra's algorithm, right? Because at every step I want to find what is the closest node to the tree that I found so far, right? And I use a heap in order to store that. And once I add an edge to my tree, then I'm going to update the heap to find what is the shortest distance from my tree to every particular node, right? So the runtime of Prim's algorithm was very similar to that of Dijkstra's, and it was something along the lines of O of E times the time for an insert into the heap, right? Plus V times the time for a delete min, right? throughout the course of Prim's algorithm, I'm going to look at the v vertices, right? And for each vertex, I'm going to pop it off the heap once, as in I've added it to my I've connected it to my tree, right? And then for each edge, I will check to see if going through this edge gives me an improved distance to that particular node, right? So in the case that what we're looking at, and the question said, say we use a Fibonacci heap, well, this will take O of 1 time, and this will take O of log n time. And therefore, the runtime overall is E plus V log V. Okay. And what about Kruskal's? Recall how Kruskal's algorithm works, right? Kruskal's, we sort all the edges first, and then we go in ascending order, like from smallest edge to largest edge. And every time we can pick an edge and not create a cycle, we do so, right? And we said that the bottleneck in Kruskal's algorithm was the sorting. It takes we're sorting E edges, right? So it takes O of E log E time to sort the edges, right? And then after we sort, everything is much faster than the sort, right? Because we saw that on average, if I want to find after we sort, doing the whole union find operations, those take on average log star n each, which is very small, which is almost constant, right? And so those are not going to affect our runtime because this is going to be the bottleneck in the runtime. And also recall that E is at most v squared, right? You can't have more edges than the number of pairs of vertices. And so we can simplify this a little bit. Log E is the same as log V, right? Because log of something is, this is just 2 log V, right? So I'm just going to replace this with V so we can compare a little bit more easily. So now let's compare these two runtimes. Okay. So let's say I gave you a graph where E is really large. Okay. So E is quite large compared to V. And so in that case, well, we would want to use Prim's algorithm, right? Because here we're just taking an additive factor of E, but here we're taking this large E and multiplying by log V, right? So Prim's algorithm, so the statement is false because it says Prim's algorithm, well, it says Kruskal's algorithm is better for dense graphs, but that's not true. Prim's algorithm is better for dense graphs because Prim's algorithm additive factor versus multiplicative factor, right? And the second part says, well, is it true that for sparse graphs, is it true that for sparse graphs Kruskal's is better? Well, sparse graphs means that let's just imagine E is basically 0, right? Well, if E is really, really small, then multiplying the small number by log V is better than multiplying, adding it to V log V, something like that, right? So Prim's algorithm is better for Kruskal's is better for sparse graphs. Okay, and that makes sense because Kruskal's, you have to do sorting of the edges. So if there's few edges, then it's going to do better. Okay. All right. So any questions about problem 1? Okay, so now let's move on to problem 4.
Did we skip the last one?
Oh, sorry. I totally skipped the last part. Yeah, so part E, I was just going to say this verbally, I guess. So part E, the question is, in an iteration of the Ford-Fulkerson algorithm on a network places, if an iteration places 1 unit of flow on an edge, then in every later iteration, that edge will have 1. And so the statement is false. I'll just give you a really quick counterexample. And the reason it's false is because in Ford-Fulkerson, we do this thing where we look at the residual graph and we do augmenting paths, right? So let's say all the capacities are 1 in this graph, and here's my S, here's my T. So Ford-Fulkerson, the first path I pick can be this path right here, right? In which case, I would say, OK, well, now this guy is 0, 0, 0, but I have to put in the back edge the residual edges, right? So it's 1 going backwards, right? So right now, this edge has a flow of 1 going through it, right? But at the next step, what do? I pick this path, right? And that sends 1 unit of flow this way. And so in the end, the two of them, basically just cancel each other out. And so this edge, this edge had 1 unit of flow going down, but then after finding this augmenting path, it actually has no units of flow on it anymore, right? And you can see that because the actual max flow in this graph is to send 1 unit of flow this way and 1 unit of flow this way, right? It doesn't use that middle edge at all, right? But it's just that through the process of Ford-Fulkerson, it's possible that an edge gets used and then gets unused later when you find a better way to use it or to not use it. Okay? All right. So let's move on to question 4. Let me see how I should be OK on time. OK, yeah. So let's look at question 4. Question 4 is the counting inversions in a permutation. So the question says, can you give me an algorithm? So it's a little confusing. It says how many permutations, but we actually want an algorithm for counting how many permutations. So I have 1, 2, 3, dot, 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 through n. And I want to say how many permutations are there of 1 through n that have exactly k inversions? K inversions. Okay. So the paper kind of defines for you what an inversion is, but just to recall, let's say I have something like 1, 5, 3, 2, 4. Then this is an inversion, this pair of numbers, right? Because 5 is greater than 4, but 5 is somehow coming before 4 in this permutation, right? And so inversions let you count basically how close a list is to being sorted, right? Because we know that a sorted list has 0 inversions, right? Every number, if you're bigger than it, you're coming after, right? And a completely unsorted list would have like n choose 2 inversions, right? So our goal here is to say, well, let's say I gave you a particular n, and I asked you how many permutations of this list have exactly 3 permutations, or have exactly 10 permutations. And so you want an algorithm that will tell me exactly how many there are, right? And you don't want a naive algorithm that just checks every single possible permutation, right? Okay. So the approach we're going to use for this problem is, does anyone have any ideas before I say it? So we're going to use dynamic programming, okay? And one intuition you might have that maybe hints at dynamic programming is that, well, the number, like permutations on n numbers is very, very related to permutations on n-1 numbers, right? Permutations on n numbers are just take a permutation of n-1 numbers and like insert that last number like somewhere into the permutation, right? And so it kind of has this nice substructure where permutations are related to smaller permutations, and so that might motivate a recursive solution. And recursion in this class is basically dynamic programming, right? We do smart recursion. We don't do naive recursion where our tree grows exponentially. We do a smart recursion where we control the number of the amount of work that we do. So using that kind of motivation, our subproblems is going to be along the lines of, I'm going to look at not all the numbers in the list, like 1 through n, but I'm only going to look at maybe the first I of them. Okay? So there are 3 steps to a dynamic programming problem. There's definition, recurrence, and finally analysis, right? So we're going to start with the definition. It's usually the hardest part of a DP problem. It's just like once I get that recursive function, then I can relate it to itself, right? And I can analyze it easily. But just getting that recursive function is usually the hard part. So I'll say all recursive functions are going to be f of ij, okay? And it's going to be defined. And it's always really important to define your recursion well, okay? Define it very precisely. So it is the number of permutations of the set 1, 2, 3 through I with exactly k inversions. Oh, sorry, not k, with exactly j inversions. Okay? So this is a very precise definition, right? I'm telling you exactly what set I'm looking at. Like a bad way of saying this would be f of ij is the number of permutations of I numbers. Like which I numbers, right? It's important that it's the first I numbers, right? And you'll see why, because when we look at adding on the next number to our permutation, it's going to be important that that number is bigger than all the other numbers. Okay, so hopefully this makes sense. And now let's think about how we can relate it to relate this f of ij to smaller f of smaller numbers. Okay, so I'll leave the base case for you guys to do, or just look at the solutions when they're posted. So we'll just do the hard part, which is the recursive case. Okay. So I want to count how many. I want to count, right? How many permutations of the first I numbers have exactly j inversions, right? So I want to say, well, I want to see what are all the ways that this could come about, right? My goal is to count all these ways that this could happen. So given any permutation of the first I minus 1 numbers, okay? So let's look at a permutation of the first I minus 1 numbers. I'll just, for simplicity, I'll just pick I equals 10, okay? And we'll generalize it in a second. So for I equals 10, it means pick a permutation of the first 9 numbers. So maybe 3, 4, 5, 6, 1, 2, 1, 2, 7, 8, 9. Okay, that's a permutation of the first 9 numbers, right? And now I'm going to look at where I'm going to put this last number 10, right? So what happens if I put the 10 at, say, the beginning of the list right here? What if I insert 10 right here? How many inversions are there going to be? How many new inversions are there going to be? Sorry. There would be 9 new inversions, correct? Because this number and all the previous numbers, this pair, this pair, this pair, they all make an inversion, right? So that means that if I wanted to, for example, if I asked you how many permutations of 1 through 10 have exactly 100 inversions, then one of the possibilities is I'm going to count all the ways for these 9 numbers to make 91 inversions, right? Do you see how that works? Like, I'm trying to count how many permutations of everything have 100 inversions, right? And one way I could get a permutation of the 10 numbers is to insert 10 at the beginning and then put 9 numbers and then put the remaining 9 numbers afterwards, right? So any way of making 91 exactly 91 inversions of these 9 numbers, if I just add a 10 to the beginning, that will make an instance where there are exactly 100 inversions, right? So this is something I have to count, right? Putting the 10 in front means that every way of taking these 9 numbers and making exactly j minus 9 permutations, that's going to be one way that I could make exactly j permutations on all the numbers. Okay, so maybe I'll write it out and it'll be a little more clear. And of course, this 10 can go here to make 9 permutations. It could also go here to make 8 permutations, here to make 7, 6, 5, dot, 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 all the way to the end to make 0 permutations, right? So here's what our recursion is going to look like. So this is going to be a summation from k equals 0 to I minus 1. And so the intuition behind k is just that, like, which slot I'm inserting it in. Okay? I'll call this slot 0, slot 1, slot 2, dot, 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 slot 9. Okay? And so inserting the 10 into slot I will create new inversions, right? So this is going to be the summation of f of I minus 1, comma, j minus k, okay? Because I'm trying to count all the ways to get exactly j permutations, right? And to get j permutations, maybe what happened is before I inserted the 10, there were exactly 91 permutations, and I inserted the 10, and that made 100 inversions, right? Or maybe what happened was, I'm going to insert the 10 over here, which creates 1, 2, 3, 4, 5, 6 inversions, and so it's all ways of permuting these numbers to get exactly 94 inversions, and then adding a 10 right there to create that 6 more to get exactly the 100 that I want, right? So it's just like there are multiple ways. There are multiple ways to get 100 inversions, and I'm just counting up all these possible ways, right? It's possible that I had 94 inversions and I added 6 by inserting the number here, or maybe it's I had 9 and I inserted it right here, and that gave me the last inversion, right? That's why I'm summing up all these numbers over here. Okay. So any questions about this problem? And so sorry, runtime and so the analysis is pretty straightforward. So remember, all DP problems, the way you analyze it is you look at the number of states of the recursive function that you have, right? And because we're going to use memoization, or we're going to build up our table, we're never going to calculate the same thing more than once, right? So the number of states in this case is going to be O of nk, right? This number ranges from 1 to n, and this number ranges from 1 to k. Well, yeah, okay. So, and then so that's the number of states that we have, right? But that's not necessarily our runtime, right? Because for each state, we're doing some amount of work to compute the answer for that state, right? And here, k is ranging from 0 to I, but I can be as large as n, right? And so we're doing, O of k, so O of n work per step, per calculation of Fij, and therefore the total runtime is going to be O of n squared k. Okay? Each state takes O of n time to compute, and the space complexity is naively it looks like O of nk, right? Because you say, well, I have O of nk states, so I must have a table to store all those entries, right? But we can actually do better, because you see that f of ij only depends on f of I minus 1 something, right? So instead of keeping around the entire table, all I need to keep around is like one row or one column. I guess it depends on which coordinate you call row and column. But all I need to do is keep around one row, I guess, of the matrix at a time, right? All I need, if I want to calculate f of ij, I only need to keep around the table for f of I minus 1 comma something, right? That entire row. I don't need to keep, the entire table. Like, if I'm calculating f of 10 comma something, all I need is f of 9 comma something, right? I don't need f of 4 comma something or f of 3 comma something, right? And so that's why we can do a little bit better on space, and we can get O of k space. Okay, let me just make sure that's correct. Yeah. Okay, any questions about this the DP problem? Okay, so you'll see that we're going to go over quite a bit of DP today. And the reason, is not necessarily because there's going to be a ton of DP on the exam. It's mostly because DP, I think, it's like one of the most important and useful concepts that you learn in the class. Okay, so when you leave this class, in 2 days, or if you're a college student, and if in like 5 days if you're an extension student, you're not going to remember how to do RSA ever again. You're not going to remember how to do the extended Euclidean algorithm. You're not going to remember all that stuff. But you're going to remember DP, I think, for a while, okay? Because it's a very useful problem-solving technique, as you see from all the examples of problems that we can solve with it. And so that's why, and we saw that a lot of students are struggling, especially with DP on programming assignment 3. And so that's why we decided to put more DP on the final review, so that make sure that you can take something away from this class that's more than memorize how to do RSA. Okay? All right, so let's move on. So the next problem we're going to do is problem 6. So problem 6 is the one on variations of Dijkstra's algorithm. So the title is called Variations of Dijkstra's, but the problem really doesn't mention anything about Dijkstra's at all. But the idea of this problem is that we know that Dijkstra's algorithm doesn't work when a graph has negative edge weights, right? We've seen an example as to why that's the case. It's because whenever we pop a node off the heap in Dijkstra's algorithm, we're saying that we found the shortest path to that node, right? And the reason we're sure about that is because every other node on our heap has a distance that is higher than the smallest node that we're popping off the heap, right? And so if everything's positive, then we know that it's impossible to to get a shorter path, because you can't go to go to a node that's further away and then go back to get to this node, because that would because if there are no negative edges, then that would definitely take longer than just going to that node directly, right? But if there are negative edge weights, then things kind of break, right? And things break because this kind of this guarantee that we have is no longer true, right? Imagine you had some kind of graph where everything was nice and positive, so some positive numbers, right? And then suddenly, you think you're almost done with Dijkstra's, right? Oh, I found the shortest path to everything, and suddenly a big negative edge comes back that takes you all the way back to the beginning. What in Dijkstra's algorithm we don't allow that, right? Because we say, oh well, I've processed these nodes, right? And so when I get to this node, I shouldn't have to go back and reprocess these nodes, because I found maybe now taking this edge, I found a shorter path, right? So that's why Dijkstra just doesn't work. Well, at least Dijkstra doesn't work with the same runtime guarantees, right? You can run Dijkstra's over, keep on going, but that wouldn't have the same runtime guarantees as every node gets popped off the heap exactly once, right? Okay. So what this problem is asking is that, well, what if instead of saying that the graph has some arbitrary negative edges, maybe in part A the graph only has one negative edge. Okay. So if the graph has only one negative edge, can we provide an algorithm that will have the same runtime as Dijkstra's, right? Recall that if I gave you a graph that has general edge weights, positive and negative, then your best bet is to use Bellman-Ford, right? Bellman-Ford works with all various edge weights, but it runs at a speed that's much slower than that of Dijkstra's, right? Bellman-Ford took about O of E times V time to compute, right? But Dijkstra's with a Fibonacci heap takes the same, only O of V log V. E plus V log V time to compute, which is much smaller than multiplying those two big numbers together, right? So what if we have one negative edge? Do we have to resort to Bellman-Ford if there's just one negative edge? And so the answer is no. We can think about how we might be able to modify either the Dijkstra's algorithm or modify the graph a little bit such that we get a correct solution in the same runtime as Dijkstra's. Okay? So the intuition behind this one, when there's one negative edge, is that every shortest path in the graph either will use this negative edge or will not use this negative edge, right? If it does not use this negative edge, then I can just remove the negative edge, and then I can run Dijkstra's normally, right? Because all the other edges are positive. If it does use the negative edge, then I can basically force it to then I can compute what is the shortest path with the negative edge by basically saying, well, let me find the shortest path from the source to the start of that negative edge, cross the negative edge, and then go from the end of that negative edge to the sink, to the target. Okay? So more formal, let me write that down. So what you're going to do is we're going to compute use the edge, and we're going to compute don't use. So if I use the edge, then, sorry, let's do don't use first. Don't is the easy case. So if I don't use, I'm going to, it's very simple. I'm going to remove the negative edge, remove that edge, right? And then I'm going to simply just run Dijkstra's normally, right? And let's say that gives me some distance. So dist sub s, to my node w. Oh, so by the way, let's say that s is our source, and then our edge that's negative is some edge uv, and our goal is to get to w. Okay, so either that shortest path, maybe it just goes that way. It doesn't use that edge, right? Or maybe the shortest path uses the edge and it goes like that. Okay, so this is like some negative number. Yeah. So if I don't use the edge, well, like the shortest path that I can get from s to the w without using the negative edge is computed by running Dijkstra's without the negative edge, right? So now what about the shortest path where I use the negative edge? Well, I want to force you to use a negative edge, right? So here's what I'm going to do. I'm going to still remove the edge, okay? But now what I'll do is I'll calculate the distance, the shortest path from S to this node U, which is the start of the negative edge, right? And then I'm going to add on the weight of that negative edge. And then I'm going to run Dijkstra's again, but starting from V to all the other nodes. And that will give me some distance from V to my node W. Okay. So this is just saying the shortest path from S to W that uses the negative edge is the, it's the concatenation basically of the shortest path from S to U, crossing the edge, and then the shortest path from V to W. Okay. And during this entire time, I remove the edge because I'm already forcing that you use the edge, so the edge doesn't really need to have to be there anymore. Okay. Okay. And so the answer is just, well, take the minimum of these two. Okay. And I know this is correct because, well, of course, every path has to either use it or not use it, and I've correctly computed both of them, right? So one of them must be the actual shortest path in the graph from S to W. Okay? All right. So let's do part B. Part B, which is completely separate from part A, says now, what if it's the case that from your node S, there are negative edges, but it's told that all the negative edges occur as the edges coming out of the source. Okay, so maybe I have something like this, negative, 10, negative 9, 4, something like that. Okay, but then everything else, all the other edges in the graph are positive. So the only edges that are negative, possibly negative, are the ones coming out of the source. So so now what's an algorithm that we can use? Well, now it doesn't work to run this anymore, right? Because there could be many of these that are negative, right? I don't want to run this part A on each of these guys, on each of those edges, right? So what I can do instead is we kind of reason about this, right? Well, every shortest path in this graph is going to use, it's going to have to use at least one of these edges. Sorry, exactly one of these edges, right? Like the shortest path from S to some node, W over here, it's going to use one of these edges coming out of the source, right? It's going to use exactly one, right? It doesn't make sense to say, oh, I'm going to come out of the source, do some stuff, and then go back into the source and then come out again, right? Because we're told the graph has no negative cycles. So how can it be better to leave the source and then come back to it and then take another edge coming out of it? Why don't I just have done that in the first place? So that says that every single shortest path from S to any node in our graph will use exactly one of these edges, right? And so what can we do then in this case? Well, let's just add some big positive number to all of these edges, right? So let's say I added 20 to all these edges. So now I get 10 here, I get 11 here, and I get 24 here, right? And now every shortest path uses exactly one of those edges, right? So I've added exactly 20 to every single shortest path in the graph, besides the one from S to itself, right? And so that all I have to do is just say add this big number to all these edges, to all these edge weights coming out of the source, and then run Dijkstra's algorithm as normal, which would work now because everything's positive, right? And then at the end, whatever distances you get, just subtract 20 from all of them, right? And that will give you the right answer. Okay? So any questions? These are pretty interesting, right? It's like your algorithm doesn't work for this type of graph, but if this type of graph is specific enough, then we can do something about it, right? Yes?
So as for the runtime, so in A, we just get essentially
It's two or three, yeah, two Dijkstra's, 2 times Dijkstra's runtime. And in here, it's just 1 times Dijkstra's runtime. Yep. Okay?
Why is it not 3? Why is it 2?
Because when you compute dist s, like this is the same dist s,
Oh, okay.
right? And then this is dist v, so that's another that's another iteration of Dijkstra's. Okay? Okay, cool. So let's move on then. So the next problem we're going to do is problem 7. So problem 7 is the largest submatrix of 1s problem. So let's see, how many have we done? We've done 1, 4, and 6 so far. Okay. Yeah, this is basically just going to be a marathon of problems until 9:40. So, yeah, feel free to, like, if you need a break or something, like, go ahead. So problem 7 is largest submatrix of 1s. So I hope you've read the problem already, but let me just clarify, give you a quick example. Something like that. Let's say that you have your matrix look like this, right? And in this case, what's the largest square matrix that is, I guess the problem starts with a m by n. Okay, so m rows, and here's n columns. And the question is, what's the largest square matrix of all 1s? And in this case, the answer is its size is 2. Right? You can either pick this guy or you can pick this guy. Okay, just square matrix of all 1s. And so, so the question is, I'm going to give you some big grade of 1s and 0s, and you're asked to find the largest square matrix, right? So what's a naive algorithm? The naive algorithm is just like, oh well, why don't I just like kind of brute force, like try to find squares of size 1, squares of size 2, squares of size 3, but that'll take forever to do, right? So we want something that runs a lot quicker than like the naive algorithm. So unsurprisingly, this is another dynamic programming problem, problem 2 of many for today. So the reason why why you might be able to recognize this as a dynamic programming problem is that the largest square, like if I told you what's the largest square, like largest square of 1s, like in say this submatrix over here, and then I asked you what's the largest, submatrix of 1s, like in a little bit bigger square, it's actually like there's going to be like a relationship between the two, right? And so that we're going to exploit how smaller problems, the solution to smaller problems can help us do the bigger problems so we don't do repetitive work. Okay, so how we're going to define our recursion is we're going to have f of ij again. And this time we're going to define f of ij to be the size of the largest square matrix of 1s with ij as its bottom right corner. Okay. So I guess I mentioned earlier, a little bit ago that the largest matrix of 1s in like say this region is related to the largest matrix of 1s like in this region, right? But it's not like that obvious how those are kind of related. Like yes, of course, if there's a matrix of if there's a 5 by 5 matrix of all 1s in here, then yes, obviously there's a 5 by 5 matrix of all 1s in this like superset as well, right? But what if but it could be that maybe there's a 5 by 5 here, but there's a 6 by 6 in this larger matrix because that 6 by 6 like utilizes some of these entries that weren't in the smaller matrix, right? So that's why when we define a recursion, we want to be a little bit more precise than just saying, oh, what is the largest, matrix of all 1s like just in this region. We want to define it to be the size of the largest square matrix of 1 such that ij is exactly the bottom the bottom right corner of that square matrix. So for example, if I called f of ij on this index over here, so like m, like maybe 1, 2, right? Then the answer would be 1. Okay, the answer is 1 because the largest. Let me just make it the example a little more informative. So let's say I changed all of these to 1, and how do I make this? Okay, so let me change. I'm just going to change some random numbers. Let me just draw a completely new example. So I just want to demonstrate that this is not the same thing as saying like the largest square of 1's like to the upper left of this particular square. Okay, so maybe you have a matrix. Here's a nice big 3 by 3. Okay, but maybe there's some zeros here. Maybe this is the 1. Okay, here we go. So let's say I called f on this index right here. So that's index 3, index 3. Right? What is f of ij? What's f of 3 comma 3? It's actually 1. Okay, it's not 3 because it is the size of the largest square of 1's that has this as the bottom right-hand corner. Right? This 3 by 3 of squares does not have this as the bottom right-hand corner, so it doesn't count. So the best square is this square, 1 by 1. Okay, and it has this as the bottom right-hand corner. Okay, and we'll see why that's going to be helpful in the recursion. Okay, because basically the idea is like we want to relate. Yeah, you'll see in a second. Okay, so hopefully that's a clarification if it's not clear from this definition right here. Okay, and so now let's see how to relate this to each other. Okay, so basically you can kind of already see that like this entry is going to be quite related to like this entry over here. Right? There's going to be some relationship between these two. I mean, and then it's going to change depending on what happens like over here and over here. Right? This entry tells you, okay, this is the size of the largest square matrix that has this as the bottom right-hand corner. Right? If it is true that this is 1, this is 1, this is 1, and this is 1, this is 1, this is 1, then that like extends to a larger square matrix with this as the bottom right corner. Right? So this entry is going to somehow involve this in some way, and there's going to be a condition, right? Because like if this is a 0, then like of course like no, this is not related to that anymore, right? But if there were some 1's over here, for example, now you see how this is going to be, there's going to be some relationship. I'll just tell you what it is. I think it's a little bit hard to think of. So the recurrence is going to be f of ij. The recurrence is f of ij is equal to the minimum of f of I minus 1 j minus 1, f of I minus 1 j, f of I j minus 1, and then whatever that is, I'm going to add 1 to it. Okay? Sorry, this is if the entry, so I'll call A as the matrix, Aij is equal to 1. And if the entry Aij is 0, then like the answer is definitely 0, right? The largest square matrix with a 0 as the bottom right-hand corner, like the largest square matrix of 1's where 0 is the bottom right-hand corner, like that's size 0, right? Okay. So why does this make sense? So basically, you can think of, basically it's like this, right? So let's say in this case. We're going to look at this. We're going to look at the size of the largest matrix with this as the bottom right-hand corner, with this as the bottom right-hand corner, and with this as the bottom right-hand corner. And we're going to take the minimum of those three and add 1 to it and say that's the best rectangle. That's the best square we can create. So I think an example basically will just show you that this is true. So let's say, let me just do this abstractly basically. So I'm looking at this entry ij right here, and it's a 1, right? Otherwise, I'm already at 0. So let's say that the size of the largest square matrix that has this as the bottom right-hand corner is 3, and this is 2, and this is 3. Okay? Then the claim is that the size of the best square matrix with this as the bottom right-hand corner is going to be 2 plus 1, 3. Okay? And you can see that that's the case because this being 3 means that I have means that in my actual matrix, which I'll draw over here, I guess. So here's 1. Here's this 1 corresponding to this 1. Okay, so all entries are over here. Fij is over here. Okay, so I don't know what this is going to be. So 1 is going to be in the bottom right-hand corner, or else this would be 0 immediately, right? And so this being 3 means that I have some 3 by 3 of 1's with this is the bottom right-hand corner, right? This is 2 means that from here, there's some 2 by 2 here that has a bottom right-hand corner, right? But no bigger than that. And then this being 3 says that starting from here, I have some 3 by 3 like that. So maybe what happens is something like that. Okay. So from this square, the largest matrix with this at the bottom right-hand corner is 2. From here, it's 3. And from here, it's 3. And so the final answer is going to be 3 because, yeah, which is going to be this over here. Okay. It's kind of like this guy is the bottom. Like if the smallest of these 3 is like the bottleneck. It tells you like where like the closest like 0 is basically like along this like in this area, right? So the smallest of these 3 numbers will basically tell you how big your matrix of 1s can be. Okay. So I know that was a little vague of an explanation, but like hopefully you play around with this formula, like you'll see why it works. Yeah. So if there aren't any questions about this, we'll move on to 9. Okay, so number 9, and by the way, these are all the questions that were most challenging for students when we did the Piazza poll, and so that's why we're going over them. But definitely feel free to ask about the other questions, and like the solutions are going to be posted like immediately afterwards. So yeah. So, but if we have extra time, which we might, we can definitely do the remaining ones that are not up on the board. Okay, so let's do number 9. Number 9 is called the hospitals problem. Okay, and we've updated the notes since the first version. Now it gives a small hint. So basically, the setup of the question is as follows: there are some like people spread out across some plane. Okay, I'll label them P1, P2, P3, P4, P5. P6. Let's say there's 7 people, okay, and I'm going to try to build 3 hospitals, okay. So K is equal to 3. K is the number of hospitals that we're trying to build, and so the goal is to be very reasonable, right? It's like I want to build hospitals, but I don't want to build like 3 hospitals like that, right? That's like bad because these people over here, they need to walk a really long way to get to the closest hospital, right? I want to spread out the hospitals as evenly as possible throughout the population, right? And another way of saying that is that I want for each person, the distance to their closest hospital be like as small as possible, right? Sorry, I guess across all the people, if you look at everyone's distance to the closest hospital, I want that number to be as small as possible, right? It would be great if I could say everyone needs to walk no more than 1 mile to get to their hospital. Right, that's the claim I want to make. I want to build hospitals in a way such that I can say everyone has to walk no more than some R miles to get to the closest hospital, and I want R to be as small as possible. Right. So part A says, well, here's like a proposed very simple, very abstract description of an algorithm that that we propose for doing this problem, and the question tells you a little bit just basically describes it to you, and your goal so your job is to phrase it in a precise way. Okay, so let me just read the paper. It says the basic idea is start with 1 hospital in some arbitrary location, and then calculate distances from all other cities. ... Find the bottleneck city and add a hospital there. Okay. So here's the more formal version of the algorithm. I'm going to start just by building a hospital anywhere. Okay, let's say I build it at P1. And then what I'm going to do is I'm going to calculate for each person what is the closest distance to a hospital. Okay. Well, there's only 1 hospital right now, so everyone's going to have to go to that hospital, right? And so I'm going to calculate what the distance is. Okay. So maybe this is 3, this is 5, this is 7, this is 2, this is 8, this is 4. Okay. And for P1 it's 0, right? Because the hospital is right on top of them. So now what I'm going to do is I'm going to look at the bottleneck person. Okay? So if I only built 1 hospital right now, I would be able to claim that everyone is within 8 miles from a hospital, which is not so great, right? So what I want to do is I want to decrease that 8, right? So what am I going to do? I'm going to find the bottleneck person, which is P3 in this case, right? And I'm going to build a hospital right on top of them. Okay? So now what happens? Once I build a hospital on top of him, what's his distance to its closest hospital? It's 0 now, right? So this 8, as this is now gone, and his distance is 0. What else changes? Well, by building this hospital, the people around them, the people around him also, may now have a closer hospital, right? So maybe for this person, they don't have to go 7 miles to the hospital anymore. They just need to go, 4 miles to this hospital. Maybe, for this person, this is not 4 miles away. Maybe this is 3 miles away, something like that. Okay? So you see, like, we build a hospital, right, at the person who is furthest away from the existing hospitals, right? And then we recompute, like, what is everyone's distance to their closest hospital, right? And then we repeat the process all over again, right, until we build exactly k hospitals. So now, who's the bottleneck? The bottleneck is this distance of 5 over here, right? So what I do is I'll just build a hospital on top of this, on top of P6, right? And then I will recompute the distances. I'm going to say, can this person get to P6 faster than where he was going before? 4 compared to, I don't know, maybe this is 3. Then that means yes. This person closest hospital is now 3 away. Can this person get to a closer hospital? Maybe this distance is 4, so no, right? So I'm going to look at all the people, and I'm going to update their distances based on this new hospital, okay? And now in this case of k equals 3, I'm done, and those are my 3 hospitals and the distances that everyone has to travel to get to their closest hospital, okay? And so what's the runtime of this algorithm? Well, I have to build k hospitals, right? So there can be k iterations of this algorithm. And at each step, what am I doing? I build a new hospital, and then I have to check all the people and say, is their distance better by going to this hospital than what it was before? Right? So that takes O of n time, right? For each person, I have stored in them what's the closest distance to their existing hospital, and then once I build a new hospital, I update it accordingly based on whether or not my new hospital makes them closer to a hospital, right? So that takes O of n time to do, and so the final runtime indeed is O of nk. Okay? All right. So now the more interesting part is this seems like a pretty good algorithm, right? Like in this example that we did, in the end, everyone was within 3 from a hospital, right? But is this necessarily the optimal? Is this necessarily the optimal algorithm though, right? Can you come up with maybe an example where where this algorithm doesn't give you the optimal answer? So you can think about that offline if you want, to try to come up with an example. But part B asks us to prove that this is a true approximation. It's not an exact algorithm; it's a true approximation. Okay, so what that means, recall, is that this is a minimization problem, right? We're trying to minimize some number, which I'll call as r, which is like the radius, almost like the distance, like the largest distance that anyone has to travel to get to their closest hospital, right? We're trying to minimize r. So let's say that r is going to be r distance. So once we calculate this using our algorithm, r is going to be r distance that we can say that everyone is within r of the hospital, and then let's say that r star is going to be the optimal solution, okay? Which I don't know what the optimal solution is, but I'm going to analyze and say r is not too far away from r star, okay? So r star is the optimal layout of the hospitals, and it is like the distance that you get from this optimal layout, okay? And we know, of course, by definition of optimal, that r star is less than r, or less than or equal to r, right? Because this is the best distance you can do, as in the shortest distance you can do. So clearly, anything our solution produces has to be greater than or equal to it, right? But our goal in this minimization problem is to say, r is bigger than r star, but it's not too much bigger. Okay? It's not like absurdly larger than r star. It's bounded above by 2 r star. Okay, that's our goal. We're trying to show that this part is by definition, and this part is what we need to show. Okay, so let's think about maybe how we're going to go about showing this. So I have to admit, I think that this problem is probably a little too hard to be on an exam. Well, if it is on the exam, it would be similar to do you remember the ski rental problem from the exam? That was proving that the greedy algorithm for that was proving that one of the greedy algorithms was correct. That was a little bit too hard, probably for a 90-minute time setting. And so this one is a little bit challenging as well. So but don't be upset if you didn't solve it. Yeah, because the argument that we're going to use is a little bit tricky. Okay, so let's talk about what our argument is. So so please remember that r star is the optimal and r is our distance. Okay. So what I'm going to do is, let's say I'm going to use squares to represent the optimal solutions choice of hospitals, and circles to represent our solutions choice of where to build the hospitals. Okay. So let's say that this is the optimal solution. It builds 3 hospitals, and it builds them in these 3 locations. Okay? So now let's say that for each location, I'm going to draw a circle of radius r star, r star away from it. Okay, so here's one circle that's centered around there. My circles are not very round today. So here's, okay, let's say those are circles of radius r star away from the place where the optimal solution builds a hospital. Okay, what can you tell me about the relationship between these circles and all the points that we've drawn?
Circles covers all the.
Correct. The circles cover all the points, right? That's just by definition of like what we're trying to do, right? We're saying that this solution, optimal, has a value of r star, means that everyone travels no more than r star to get to their closest hospital, right? So in particular, if I take every hospital and look at the circle of radius r star around it, everyone has to be within the union of those circles, right? Or else you would be more than r star away from your closest hospital, right? So, okay, so good. That means that all the points are covered, okay? So now let's look at our solution, okay? So maybe our solution picks something like this. Something like that. Okay, maybe that's our solution. We pick those 3 instead of the optimal, which is to pick those other 3. So in this case, what happens is you can see like within this circle, I can say so this so there's like every circle has exactly one as in like I can assign I can create like a like a bijection between the circles and like the point that I pick. So here's a circle, here's a point that's inside that circle that I picked. Here's a circle, here's a point that's inside the circle that I picked, and here's a circle, and here's a point inside the circle that I picked. So it's like so in this case, what I can do is for each circle I can pick exactly one of the hospitals that I built, like to be say like part of this circle, and this hospital will be part of this circle, and this hospital will be part of this circle. So sorry, that's probably not really clear, but basically the idea is like look at all the big circles that I drew, and then I want to say like there's a way to allocate the hospitals that I built so that each of my hospital corresponds to exactly one big circle that it's in. Okay, so you'll see why this is useful in just a second. So basically like I drew some circles, right? Like that's the covering by the optimal solution circles, and I want to say that like there's a way for me to say, oh, this one, this hospital that I chose is in this circle, this hospital that I chose in this circle, this hospital, like that. Okay, I want to say that there's a way to assign each hospital that I built to one of these like optimal circles, such that like there's a one-to-one mapping. Okay.
It's impossible to have it so that.
It's possible that the two of them are going to be in the same circle, but I'm just going to do this by casework. Okay, so my first case is going to be something like this, where all the hospitals I choose are like in different optimal circles. Okay, and my second case is going to be where maybe there exists 2 hospitals that are in the same circle. Okay, so we're going to prove that this bound is true in both of those cases. All right. So the first case where all the hospitals are like spread out across the many optimal circles, why is it true that everyone has to be within a distance of 2 r star from the hospitals that we built? Why is that the case? Well, that's just by like the triangle inequality, right? I know that everyone is within a distance of r star away from one of the optimal hospitals, right? But my hospitals are in the same circle as one of the optimal hospitals, right? So therefore, it is certainly true that any person can get to one of my hospitals in less than 2 r star distance by just going to their closest hospital, which costs r star distance at most, and then go from there to my hospital. But my hospital is like within a circle, right? Like each circle, which corresponds to one of the optimal hospitals, right, has one of my hospitals that is within like in that circle, right? So by the triangle inequality, I can just go to the optimal hospital, but there's no hospital there, and then I'll move, and then I'll go to my hospital, right? And that will take at most 2 r star distance, right? So that's the case where it's basically like every optimal circle has one of my hospitals in it. Okay, yeah, I think that's a better way to explain. Like every circle needs to have at least one of my hospitals in it. Okay. Okay, so that's the first case, and yeah, for certain we get that everyone's distance to their closest hospital, to my hospitals, are no more than 2 r squared, 2 r star, right? So now we're going to do the other case, which is what if I built two hospitals that were like both within the same circle, okay, same optimal circle. So maybe I built this hospital over here, and these two hospitals are within the same circle, okay. So the argument that we just made earlier, using the triangle inequality, that had nothing to do at all with our algorithm that we did from part A, right? That was just like, if you gave me any bogus algorithm which could put exactly one of your hospitals into each of the optimal circle, like big circles, like that would be a true approximation. That's like, had nothing to do with the algorithm itself, right? So what we're going to do here, like in our second case, is like we're going to have to use this algorithm in some way, right? We have to show that, yeah, no, if you just pick randomly, you're not going to get it, right? It's only if you use our algorithm, then this analysis will hold. So here's like the really clever argument as to like why this is the case. So imagine that I picked two hospitals that are within the same circle, right? And this circle, remember, again, is a radius r star, okay? So what does that tell you about these two hospitals themselves? They're within 2r star away from each other, right? Because they're in the same circle. Why would my algorithm pick one hospital to be within 2r star of another hospital? Recall how our algorithm works, right? Our algorithm just, at every moment, it finds the person who is the furthest away from any hospital and then builds a hospital on top of them, right? Which means that everyone's like distance to their closest hospital can only like decrease, right? Like, as new hospitals are built, my distance to the closest hospital will decrease, right? Because I'm picking the person who is the furthest away and making that person 0 away from a hospital, right? So effectively, I'm taking the person with the largest distance to the closest hospital and removing him, and then putting updating the distance accordingly, right? So at every step, there's the distance of any person to their closest hospital is like non-increasing, right? It definitely at least goes down, at least doesn't go up at every step, right? So if I picked two hospitals that are within 2r star from each other, that must mean that this distance that I'm trying to optimize is already lower than 2r star, right? Because I would never pick a hospital that is within 2r star of another hospital unless everyone can already reach a hospital within a distance of 2r star. Did that make sense at all? Okay. My algorithm keeps on improving, right? The distance, each person gets only closer to hospitals as the algorithm goes on, right? So if I build two hospitals that are within 2r star of each other, that must mean that everyone can go to a hospital within 2r star of each other, or else I would have built it, on top of, or else I would have, basically like, or else, I would have built a hospital to, I wouldn't build two hospitals so close unless it was already the case that everyone, could reach a hospital that's close to them. Okay, so yeah, you can read the solution a little more in detail. I think I just like kind of hand waved it. But yeah, that's problem 9. Any questions? I think it's a little bit too challenging probably to be like to be on like the exam. But yeah, it's possible, of course, because like there has to be challenging questions for some of the students in the class. Okay. So now let's move on to question 11. So we have 6 problems left, and we have about an hour. That's good. Okay. So problem 11 is this problem of finding well-nested strings. And so in the problem, we're given like 4 types of symbols. So we have open parentheses, close parentheses, open angle brackets, and close angle brackets, right? And our goal is we're given some string. I don't know. This is not the same example as on your sheet, and some string like that. And your goal is to say, well, this string has length 1, 2, 3, 4, 5, but it is not well nested, right? Well nested means like intuitively exactly what it sounds like. Like the three criteria I think are on the paper. You can just read it. But this is not well nested, right? So the question is, what is like the length of the smallest string that contains this as like a subsequence? Okay, so subsequence means that things don't have to be next to each other, right? It just means like, can you find me a string such that when you scan from left to right, you can find an open parens and then a closed parens and then an open angle, closed parens. Okay, so in this case, like just by inspection, the correct answer would be something like this, right? So maybe this is one possible answer. Okay, and this string has length 1, 2, 3, 4, 5, 6, 7, 8. So we would output 8 as our answer. Okay, it's the length of the shortest string that contains this as a subsequence, and you'll see it's a subsequence, right? You know, this like open, close, open, open, close, like open, close, angle, open, close. Right? It's a subsequence. It doesn't have to be contiguous. Yes.
Oh, it does have to be contiguous.
It doesn't have to be like the order has to be contiguous, but it doesn't mean like you need to make, because like it wouldn't be possible to get something like that's exactly like something that's well nested with this like exactly as a substring, right? Because you would have to like insert something here, or you have to insert something there, but then you have to like insert, right? So it wouldn't be possible to get a contiguous block. So we're asking for subsequence. Okay. So now, no surprise that this is another dynamic programming problem. So this dynamic programming problem is, but why is it a dynamic programming problem? It's because intuitively what you have to do in this problem is like, I'm going to start from the left to the right, and I'm going to look at each character. Okay, let's look at this open parens, for example. So in a well-nested string, there has to be some matching closed parens to this open parens, right? And what are some possibilities that I can do to deal with this open parens? Well, maybe the best thing to do is just like ignore the fact that you know what's coming up. Maybe the best thing to do is just like close it immediately. Okay, so I'll just like pay a cost of adding an extra character and just like close it immediately and then move on with the rest of the string. Maybe that's one thing I should do. Maybe the best thing to do is I should try to scan and look for a closed parens and then match this open parens to this closed parens, and then I'm done with, and then I just recurse on whatever's inside and whatever's outside. That's another possibility, right? So it kind of seems like a dynamic programming flavor problem, because with that reasoning, it's like I'm looking at, if I looked at this whole thing as a subproblem, I can recurse to this as a subproblem, and to like whatever string comes back here as a subproblem, right? And I can recurse, if I added this parens in, I can recurse to this as a subproblem, right? So it already has this kind of nice structure where if I define my function like this, as in say f of ij is equal to the minimum number of characters to add to, say, the string from like the ith character to the jth character. And I guess in this case, it doesn't really matter to say if you include the jth character or not, as long as you're consistent with your notation throughout. So let's just say that we include the jth character. I don't remember how the solutions do it, but it'll be defined clearly. Okay, so that means that, and assume our string is s, and its characters are s1, s2, s3 through sn. Okay, so the answer that we're trying to compute is f of 1, n, right? First character to the nth character. Minimum number of characters to add to s of I through j to make well nested, right? Oh, sorry, it's not the minimum number of characters to add. It's the minimum number of characters like total, right? Like it's not like I have to add 3 characters to this to make it well nested. It's just like what's the length of the final string that has it as a substring, right? That's the subsequence. Okay, so let's use the reasoning that we just talked about, to get a recursive formula. Okay, so f of I comma j is going to be equal to something. So first thing that we notice is that if whatever my example is, string that I give you, let's say it starts with some kind of closing bracket. Okay. Oh, sorry, I did define for you s at a j, right? Let's say it starts with some closing bracket. Okay. Then what is the only way that I can deal with this closing bracket? Add an open bracket, like say just immediately before it. Right? There's like no other way I could do anything about this. Right? Remember, I'm only looking at this substring, right? From the ith character to the jth character. There could be other things, but I'm blind to those because my subproblem is only these characters from the ith to j, right? So if I want to deal with this not being well nested right now, the only way I can deal with that is by adding an open parentheses, right? It doesn't really matter like if I add it here or like anywhere before. Like I have to add at least one character to make the open parens to well nest this guy, right? And once I've done that, then I can basically just ignore these guys, right? Like they're well nested, and so I recurse on this over here, right? So that means that in the case where the string at I is equal to a closed parens or a closed angle, what my recursion is very simple. It's just going to be 2 plus f of I plus 1 j. Okay. 2 is because now I'm looking at this string I plus 1j, right? And whatever is the best way to make this well nested, I'm going to add 2 characters to that, right? Because I've taken away 2 characters, one that was there and one that I added. Okay, so it's 2 plus that. And then, so what's the other case? Well, the other case is maybe my string from I to j is something that looks like this, you know. Let me do one where it's a little more informative. So, okay, something like that. Okay. So now, what if my first character is not a close or is closed bracket? Maybe it's an open bracket, right? Then what should I do? Well, if it's an open bracket, there are 2 ways that I can deal with this and close it and make it well nested, right? Either I just say, oh well, let me just close it right away. That's a possibility, right? Like maybe it's best that this open bracket gets matched with nothing and just gets closed by itself. That's a possibility, right? What if I had a string that looked like this, for example, right? And the best thing to do about this open bracket is just to close it immediately. If you try matching it with something, you're just going to end up doing more work. Right? The best thing to do is just like close it off immediately, right? So, and so that's one possibility. Right? One possibility is just like recurse on I plus 1 to j and close it off. Okay? So it's always going to add 2 characters. I'm going to have the 2 on the outside, minimum of a couple things, right? So one possibility is f of I plus 1 j. Maybe I just close it off immediately, and then I'll just recurse on the rest of the string. Another possibility, probably more commonly, is I'm going to take this open parens and match it to one of the closed parens of the same type later on in the string, right? So maybe I match this with this guy. Or maybe I match this open parens with this closed parens. I don't know which one I should match it with, right? So what am I going to do in dynamic programming? I'll just check them all. Right? I'm going to say, try matching these together and then recurse appropriately. Try matching these together and recurse appropriately. So when I match, say, this guy and this guy, what do I recurse on? I recurse on whatever's inside and whatever's left behind afterwards, right? So let's say that the closed parens that I try to match against is at the kth character, right? Then I'm going to take a minimum over all of these, basically, so I'm going to look at over all k's of the property that, so this is the case where Si is equal to an open parens, an open angle bracket. So I'm going to, my notation is kind of bad here. So, okay, so I'm going to say it's the minimum between f of I plus 1j and the minimum over all k such that S of k like is equal to like the corresponding closing bracket of Si. Right? I'm going to look at all these possible locations k, where if I is an open parens, I'm going to look at all the closed parens. If I is an open angle, I'm going to look at all the closed angles. Right? And I'm going to look at the minimum of the minimum over all that of what. I'm going to just erase these cases because it's getting in the way. So minimum of what? Remember, what happens is if I pick this, for example, to be the corresponding closing of this ith character over here, then I'm going to look at the inside and look at what's remaining, right? So it's going to be I plus 1, k minus 1, f of I plus 1, k minus 1, plus f of k plus 1, j. Okay? Does that make sense to everyone? So this is saying how many characters do I need to like, basically, I've matched this ith character to this jth like corresponding close, right? And so I have to now look at in between and afterwards. In between is from I plus 1, this index, to k minus 1. And then afterwards is k plus 1 all the way through j. Okay? Okay, cool. And so that's our final recursion. So it's the minimum of these 2 things. And let's just analyze the runtime real quick. The runtime is the number of states is O of n squared, right? And for each state, how much work am I doing? I'm looping through like the entire string, possibly, right? So at each state, I'm doing O of n work per state. So that results in an O of n cubed algorithm. Okay? And that's the runtime. And the space complexity is O of n squared. Right? That's just the number of states. And I cannot save any space by like storing only part of the matrix because every recurrence uses like a lot of other things like inside. Like this uses I plus 1, this uses I plus 1, this uses k plus 1. So I can't just store like one row, one column because each recursive call calls like a bunch of various things from different parts of the matrix. Okay? All right, any questions about this problem? This is a little tricky. This was on this is a problem on the P set from like 2 years ago on DP. Yeah, but hopefully, important thing to note, notice how like it's always 2 plus, right? And that makes sense because every well-nested string is going to be an even length, right? So you're always adding 2 at each step. And the base cases are going to be like 0, so you're not. So all the numbers are going to be even. Okay. All right. So let's move on to number 13. So, okay. So, oh, actually, I only did half the problems now. Oh, okay, whatever. Okay, so problem 13. This one is what again? The NP completeness problem. Okay, so the this is the NP completeness problem. So we gave you 2 like problems, and we're asking you to show that each of these problems are NP complete. So how do you show that something is NP complete? We have to show that it is NP and that some other problem in NP that is NP complete reduces to it, right? So in NP, that means there exists a short certificate, right? And 2 is reduce from another NP complete. Okay. So let's look at the first one. The first one is something called subgraph isomorphism. And so there's kind of fancy definition, but like here's a really simple example to help you understand. So what it's really doing is just like looking for small graphs in big graphs. You know, something like maybe I have some, some big graph. Okay, here's my big graph G, and here's my small graph H. And so in this case, I'm trying to find this, this thing called a 4 cycle, like in my graph G. And so here's an example of a 4 cycle. Right, that's an instance of this graph in here. But here is not an example of a 4 cycle. You see how these 4 nodes, even though there is a 4 cycle among them, it has to be like an isomorphism. So it has to be like edges that are there are here as well, and edges that are not there are not there. So there are no edges here, right? So this is not an instance of a cycle, well, it's like strictly because this also has the diagonal edges in there. Okay? So we're looking at the problem where it's like exact match. Okay? What's there is there, and what's not there is not there. So this is a clearly an NP, right? Like if I asked you, is there an instance of this graph in here? You just tell me what it is. I give you the nodes. Nodes U, V, W, X is that particular graph, and I can check it very quickly, right? But so now the hard part is how do we reduce this from another NP complete problem? So is there another problem that we know is NP complete where the goal is to like take a graph and find some type of subgraph that satisfies, it's like some kind of subgraph?
Click.
Yeah, the click problem, right? The click problem is exactly, I guess it's the k-click problem, right? The k-click problem is saying, does there exist a click of size k in our graph, right? And this is NP complete because we can do it in n to the k time, right, by just checking all like combinations of k nodes. But like that's not like polynomial. That like depends on k, right? So this problem can k-click can reduce to our problem of subgraph isomorphism, right? So if I asked you, is there a k-click in this graph, that's equivalent to saying, is there a subgraph of this graph that is exactly the k-click or whatever size click, right? Okay. So I'm just trying to find, like, say this is a 5-click. I'm just trying to find, if I asked you, is there a 5-click in this graph? Same thing as saying, is this isomorphic to any collection of vertices in that graph? Okay. So finding a k-click is the same thing as saying, construct this graph, which is like click of size little k, and then trying to find an instance of that in your big graph. Okay. So that shows that our problem of subgraph isomorphism is harder than the click problem, right? And it makes sense because like in the click problem, all we're trying to do is find clicks, right? But in the subgraph isomorphism problem, it's like saying, oh, maybe I'm going to ask you find, this structure where it's like the click but minus one edge. That's like a harder problem. It's like you have more possibilities, right? Like, I can ask you to find any subgraph, using the subgraph isomorphism problem, but the click problem I can only ask you to find clicks, right? So the subgraph isomorphism problem is strictly harder than the click problem because the click problem is a special case of it. Okay, so that shows that it's NP complete. Okay, so the second problem that we're going to look at is this thing called the 4 exact cover. So the setup for the problem is as follows. I have a bunch of elements. So I think the problem says like x, right? So I'll have x1, x2, ... through xn. And then I have some collection of sets, s1, s2, ... s, I'll call it sm. Okay? And then we have the property that each si is of size exactly 4. Okay? And the size of x is exactly 4 times like some number q. Okay? So x has some multiple of 4 elements. Maybe x has 40 elements. And then each of our sets has exactly 4 elements. And our goal is to say, find me a collection of these sets, a collection of 10 sets, right, such that those sets like form a partitioning of the x's. Okay? So partitioning means like non-overlapping, right? So maybe, maybe the final answer is like, s1 is equal to like, x1, x3, x20, and x, x39, something like that, etc., all the way to s10. Maybe this is like x2, x7, x15, x23, something like that. Our goal is to like say, pick 10 of these guys such that, all the x's that are involved like form a, like this is the partitioning of the x's. Okay, so that's the question, and it turns out to be an NP complete problem. First, why is it an NP? Well, the question asks, I guess, for the collection of sets. So I can give you the collection of sets, right? I can give you those 10 sets. You can quickly check for me that none of them overlap and that every element is covered. So that's an easy way for me to convince you that yeah.
So when we're talking about, when we're showing that it's an NP by showing that there exists a short certificate,
yeah,
often is it like sufficient to just like state flatly, like given a solution, you can, check?
Yes, so your solution has to be like checkable in polynomial time, right? Like for example, the question that's saying maximum click is not in NP because if I said, hey, check for me that the maximum click in this graph is of size 5, like how would I prove that to you? How would I prove to you that there does not exist a click of size 6 in the graph, right? So that would be like, I can give you a click of size 5, but that doesn't prove that there does not exist a click of size 6, right? So finding a specific size click is an NP complete problem, but finding the maximum click is not. Okay, it's NP hard because it is just this, not an NP. Okay, all right. So how does 4 exact cover relate to the other problem that the paper mentioned, which is 3 exact cover? Well, the relationship is that so we tell you that 3 exact cover is NP complete. So 3 exact cover is the exact same layout, like setup, except now instead of having 4 Q sets and each set being size 4, it's 3 Q sets and each set of size 3. So here's like basically the visual as to how this reduction happens. So what happens so my goal is to say that I'm trying to show that 4 exact cover is hard, so I'm going to take 3 exact cover and reduce it to 4 exact cover, right? I'm given that this is hard. So if I can reduce it, then that shows that this is hard, right? Okay. So how am I going to do that? Well, let's say I gave you an instance of 3 exact cover. Okay, so here's like what an instance of 3 exact cover might look like. So maybe I gave you 12 nodes, right? And I give you some sets of size 3. They overlap and stuff like that, something like that, right? And the goal is to say, can you find me a collection of these 3 sets, exactly 4 of them, right, such that no 2 sets are overlapping? And in this case, with this really messy example, you can see like this set, that set, and these 2 sets. That's an exact cover, right? Okay. So how can I reduce this to a 4 exact cover? Well, in this problem, what I was doing was I was picking 4 sets of size 3, right? So what am I going to do? To get it to be 4 exact cover, I need to make it sets of size 4, right? So that means that every set I need to add a new element to, right? So what I'll do is I'll create, so remember this is 3, right? And this is q. Right? There are q. There's each set of size 3, and there are q, like 3q of them, right? And so what I'm going to do for each set si, sorry, I'm going to create some dummy nodes, okay? So some dummy elements, and those dummy elements I'll call y. So I'll create y1, y2, all the way through yq. Okay. So now, if I include those dummy elements, it would look something like this, right? There would be q of those dummy elements. And now what I'm going to do is, for each of these existing sets, I'm going to create a for set with each of these dummy nodes. Okay? So one set is going to be this. These 3 nodes and that node. These 3 nodes and this node. These 3 nodes and that node, etc. That for each set here, I'm going to create q new sets. Okay? And replace those old sets. Because now sets of size 4. Right? So that's what I'm going to do for all of these sets. So now, originally, maybe I had S1 through Sm. Right? That's m sets. And now I will have mq sets. Okay? Because for each set S1, I'm going to create S1, S11, S12, S1q. And then S2, S21, S22, S2q, SM1 through SMQ. Okay? And now the claim is that like the 4 exact cover on these sets is exactly like, now solving 4 exact cover on these sets is equivalent to solving 3 exact cover before, right? Because now it's like saying each of these 3 sets, like I have a freedom to pick one of the dummy nodes to use, right? And so I can pick whichever dummy node, like I can pick whichever dummy node I'd want, and then like say maybe these 3 elements and this one, right? And I'll pick these elements and this guy. And I'll pick these 3 and this guy, and these 3 and this guy, and that gives me a 4 exact cover, right? So yeah, I'm not going to be really formal about the proof, but like hopefully you see how the logic works, right? Adding dummy nodes to make size of sets of size 3 into sets of size 4, yeah.
So you have q dummy nodes,
Mhm.
and you're saying that for each of our m sets, you create, get rid of the old set and
Yep.
create
Q new sets for each set.
So why don't you just create, like for each of our m sets, like one new set with one, like.
But like then how many? But then like I want to create exactly k new nodes, right? I don't want to create m new nodes. I think maybe what you're saying is like, why don't I just say for each set I'll create a new dummy node that like that set uses, right?
Yeah,
But I want exact cover, right? So some of these sets I'm not going to choose. So I don't want their dummy elements to be uncovered at the end.
Okay.
Does that make sense?
Yeah.
Okay. Okay, cool. So that's a problem. So unless there are any questions, we're going to move on to 15. So it seems like we have 30 minutes left and 4 problems. That should be fine. Okay, so what is 15 again? 15 is the random walk question. Right, great. So recall from lecture, let's recall the SAT problem in general. Okay. For example, 2SAT and 3SAT, right? So in 2SAT and 3SAT, the idea is that I have a Boolean clause, like a sequence of Boolean clauses, right? And each of the Boolean clauses is going to be basically, like x1 or x2, and like x3 or like not x2, like etc. Right? It's going to be the and of a bunch of or clauses, right? So in order to satisfy this clause, like it means that at least one of the variables in each of the clauses has to be set to be true, right? Either x1 is true or like maybe x2 is false, which would make this true, right? So that's the 2SAT problem. The 3SAT problem is just equivalently, except now each clause, maybe has up to three variables in it. Okay. So in class we saw an algorithm for 2SAT, right? Our algorithm involved a random walk. Our algorithm says, let's suppose that there was some satisfying assignment, right? Let's suppose that our satisfying assignment was x1 is equal to something, x2 is equal to something, xn is equal to something. This is a satisfying assignment. Okay. And what we're going to do is we're just going to start with some random assignment, right? We started with like some y1. I'll just set them all to false. And what we did was just said, OK, at every step, what we're going to do is we're going to find an unsatisfied clause, right? And we're going to flip one of the variables at random in that unsatisfied clause, right? So here's my solution. Here's the satisfied solution. It's not the same right now, right? So I'll just find, well, this is, well, if this satisfies, then I'm done. If it's not satisfied, then there must be some difference between this and this, right? Therefore, I'm just going to find a clause that's not satisfied, and I'm going to pick one of the two variables in that clause at random, and I'm going to flip it, right? And that's going to make me either go one closer to here, or it's going to make me go like one further from here, right? Either I flipped one that made me the same as the satisfying assignment, or I flipped one that made me more different from the satisfying assignment, right? So in that case, what we said was, our solution space was like representable by like a random walk, right? Where we're on 0, 1, 2, 3, ... to n, right? And we're saying this represents how many variables am I the same as this satisfying solution, right? N would be, yay, all the variables are the same. 0 means all the variables are exactly the opposite of that satisfying assignment, okay? And so in the 2-sat problem, we said that, oh, well, we go left and right with probability 1/2, right? This is like the worst case. Like, it could be true that maybe maybe one of my clauses is x1 or x2. Maybe I set x1 to be false and x2 to be false, but maybe the satisfying assignment has this to be true and this to be true. Well, in this case, I can flip either of them, and I will get one closer to the satisfying assignment, right? But the worst case is that like I have to pick exactly the right one to flip. I can't flip the other one, right? So the worst case is kind of like this random walk where you go left and right with probability 1/2. You could go right with probably more than 1/2, but the worst is like probability 1/2 this way, probably 1/2 this way. Okay? And so in class we saw that this kind of random walk, the expected number of moves, right? Expected like moves until you reach n, that was on the order of n squared, right? It was like n squared minus I squared, something like that, right? So what we're going to do in this problem is we're going to show that, well, why don't I just try the same algorithm for 3-sat, right? But we know that 3-sat is an NP-complete problem, right? There shouldn't exist this algorithm that runs in some polynomial time, right? So we're going to see exactly why you can apply the same algorithm to 3-sat, but your runtime is now exponential, okay? So part A asks you to show that now look at a random walk that's very similar to what we did before, except now, again, it's 0, 1, 2 through n, but now it's like left with probability 2/3 and right with probability 1/3. And let's say if you're at 0, then you just always go to 1. Okay? Why is this harder to reach n in that case, right? Because here's like equal probability of going both ways. Here's like you have a much higher probability of going to the left and like making back no progress rather than making progress towards n, right? So the problem asked you to verify that the formula that we give you is correct. So how would I set up a recurrence where ti is the expected number of moves until I reach n? Well, I would have a formula that's like this. T of I is equal to, so from any point I, the first thing that can happen to me is either I move to the left with probability 2/3 or I move to the right with probability 1/3, right? So with probability 2/3, I'm going to move to the left. And in that case, I'm going to take ti plus 1, like more steps after I've done that in order to get to n, right? So ti minus 1 plus 1, right? The other case is I move to the right, in which case now that takes ti plus 1 steps on average. Right. That 1 is to account for the fact that I made this particular step, so I pay that cost of 1, and then it's however many steps are now required from that point onwards. So this becomes, 2/3 t of I plus I minus 1 plus 1/3 t of I plus 1 plus 1. Okay. And then so I have to verify. It's simple. Just verify that the equation we give you satisfies this recurrence, and then also we have that t of 0 is equal to like t of 1 plus 1, right? That's a special case because we always go to 1 from 0. And also we have the case that t of n is equal to 0, right? And then so just verify that our formula gives you that holds for this example. And then part B is basically what I explained already. This algorithm, so our formula was like t of I is equal, and this has been updated a couple times. So this is the correct formula. But you'll see basically the main problem is this, right? You have 2 to the n. And so on average, in the worst case, maybe I start from t0, it'll take me on about 2 to the n moves to get, 2 to the n iterations on average to get to a satisfying assignment, and that's not good, right? So that shows that the same algorithm that we use for 2-sat, which ran in O of n squared time, does not work for 3-sat. Okay? All right. So that is problem 15. And so now we have, yes?
Quick question. So part A asks you to verify that the formula is correct, and you can just do that doing like when you
Yes.
do all the substitutions.
That's right.
Part B says, suppose we attempted to use the same random walk algorithm for 2-sat on 3-sat, and it asks like when you apply the same algorithm, why
It's not
it's
polynomial,
not-
right?
not- and we sort of proved that.
Yeah, sorry, I kind of just did it the other way around, right? I just like said I first showed you why why you know like if like like why 3. I guess I kind of showed you first like why this doesn't work for 3-sat, right? Because I said like, well, you know, basically what's going to happen is like in 3-sat, in 2-sat, we said that the expected number of moves until we get to the final answer, like a satisfying answer, is like O of n squared, right?
Yeah.
And that's because, you know, in 2-sat, our formula for Ti was like T of I is equal to like n squared minus I squared, right? But here in 3-sat, if we use the same reasoning about moving between states, our formula that we get is like T of I is equal to 4 times 2 to the n minus 2 to the I, right? So now we can't have the same bound that there's a polynomial time expected number of moves, because in the worst case, there's an exponential number of moves that we have to take before we reach the satisfying assignment. Does that make sense?
Yep.
Okay, cool. All right, so now it's so now 3 problems left, 16, 17, and 18, and we have like 25 minutes. Okay. Yeah, okay. So, all right, so 16, I think, is probably my favorite question, because it's like pretty cool. There's, you know, you don't really think about this on an everyday basis, but you know, there is an algorithmic problem behind some of the things that you see every day. So 16 is called the 2 waiters problem, and basically the setup is the following: you have a restaurant and you have some tables, and the tables are like labeled 1, 2, 3, 4, 5. Let me just say there's 6 tables, okay? And there are 2 waiters. And the waiters will start at table 1 and table 2. Okay, that's just by definition. And what's going to happen is, as time goes on, like the tables are going to start raising their hand and calling for a waiter. Okay. So maybe what happens is, and I call those the queries. Q1 maybe is 3. Maybe Q2 is like, maybe table 3 calls for waiter first, and then table 4 calls for waiter. Maybe then, you know, table 2 calls for the waiter, and then maybe, you know, table 6 calls for the waiter, etc. And I said there are m of these. Okay. So don't think too much outside the box. It's like one table calls the waiter, and then the waiter goes there, and then a little bit later another table calls. Like, it's not like, oh, what happens if two people call the waiter at the same time? Like, it's just a simple problem where one person moves at a time. Okay. So now the goal here is that I want to minimize the total amount of walking that the waiters have to do. Okay, I don't want them like, you know, walking around the restaurant too much because they'll get tired, right? So the goal is that, okay, but you know, some omniscient being has told you that today this is the list of all the tables that will need servicing. This is the order in which the tables will need servicing. Okay, and they want you to plan the route, like basically like when table 2 wants to be serviced, you should be able. You tell me which waiter 1 or waiter 2, do I move to service table 2? Okay, and the goal is, you know, throughout the entire day to minimize the total amount of walking that the 2 waiters have to do combined. Okay, so any questions about the problem statement? Okay, so and it's clear that like there's some optimization going on here, right? It's not always best, you know, like, well, is it best to always just say at every step, you know, if table 2 calls, just move the waiter that's closest to table 2, like to that table. Is that the best thing to do? So that's exactly what part A tells us to show. Part A says, show the greedy algorithm, which is exactly what I described, is not optimal. Okay? So the greedy algorithm, again, is every time a query is made, just move the waiter that's closest to it to that table. And intuitively, there's an explanation for why the greedy algorithm is not correct. The greedy algorithm, it's very short-sighted, right? All it does is say, oh, look at that request that's coming up and service it in the best possible way right now. But it doesn't look at all as to what comes next, right? Can you think of an example of a situation where what comes next will influence your decision right now? Right. So I'm going to give you an example. Unless you have an example.
Well, I was just going to say, the problem says that like each table is like table I is located at xi, yi.
Yeah.
So like that means that the tables are sort of like arranged in a diagonal, right? Or
No. It's just
line.
xi, y just means like some random x, some random y. Like some coordinate x, some coordinate y. Yeah, just on the plane. In no particular configuration. Okay. Okay. Cool. So Yeah, so I guess I was saying, yeah, maybe you can think of a situation where it's better to move a waiter that's further away from, like, let's say I'm requesting the waiter right now. Maybe it's better for the waiter that's further away to come to me instead of the waiter that's closer to me, because when the waiter that's closer, because maybe the table that the waiter is closer to me right now, it's going to get serviced again, like, immediately afterwards. So I don't want to make that waiter move back and forth. Instead, just one waiter comes to me from afar, and that will solve my request. Okay. So here's a very simple example to show you that. So here's the coordinates. So here's like the x, y, basically. Here's 0. This table 1 is at 0, 0. Table 2 is at 3, 0. And table 3 is at 5, 0. And they just happen to be on the same line, but they could be anywhere. So now let's say the requests that comes in are q1 is equal to 2. Sorry, I'm going to flip these because I just want to be consistent with the fact that waiter 1 starts at table 1, and waiter 2 starts at table 2. Okay? So let's say the first request that comes in is table 3, and the second request that comes in is table 2. Okay, that's it. That's the whole thing. So when this request comes in, what's the greedy algorithm do? The greedy algorithm says, oh, who's closer to table 3? The picture doesn't show it, but waiter 2 is closer to table 3, right? Only 2 units away as opposed to 3 units away. So what I'm going to do is I'm going to move waiter 2 to this table, right? Now the second request comes in, and the request is for table 2. But now who's closer to table 2? Waiter 2. So waiter 2 is going to move back to table 2. And so total, what's the distance that waiter 2 has traveled? Well, the total distance traveled between both waiters is 4, right? Waiter 2 did 2 and 2. But what is the optimal solution? The optimal solution would have just been when table 3 was requested at the beginning, why don't we just move waiter 1 over, okay? That pays a cost of 3, which is more than what we could have by if we had moved waiter 2 over, right? But now, when the second query comes in for table 2, I pay 0 because someone's already at the table, right? So this is 4 versus 3. So this is 3 versus 4. So this is a better way to do this, okay? And so now we're going to, part B asks us to actually compute find an algorithm that will solve this problem exactly, okay? So does anyone have any thoughts? This is the last problem I promised that's going to be DP. So, okay, so it's DP. And so the intuition as to why this is DP is that there's kind of like a substructure here where it's like, okay, if I told you, like at each step, I'm trying to make the choice as to whether or not send waiter 1 or waiter 2 to service this table, right? And once I've done that, then I'm really in the same problem as I was before, except now what's different? I'm looking at a smaller list of queries, right? And the waiters are at different starting positions, right? So that motivates a solution where we have a recurrence where we kind of go through where we store where the waiters start and which queries we're looking at. Okay. But one thing before we do that, in this problem we gave you like the runtime that we want, right? The runtime that we want, we told you was O of n squared m, correct? And we told you the space we want is like O of n squared. So just from the runtime. And if I told you this is a DP problem, it gives you a huge hint as to how to do the DP, right? Because with the runtime, it tells you how, basically, how many variables you should use in your recursion, what time you should be using in each step of the recursion, right? So if this is the runtime, then what are the possible recursions I can have? Well, I could have something like this: f of I, j, k is equal to maybe the minimum of some constant number of things. Right? Maybe I have 3 variables. I ranges from 1 to n, j ranges from 1 to n, and k ranges from 1 to m. Right? That's a possibility. The runtime would be n squared m, and then each item takes O of 1 time to calculate. So this whole runtime would be O of n squared m. Right? Another possibility is that this is f of ij, where say so I ranges from 1 to n, j ranges from 1 to m. And then to compute it, I'm maybe taking the minimum over n different things. Right? There's another possibility. The runtime would be n squared m. Right? So if I gave you the runtime of a DP problem, it makes it easier for you to determine what's a good solution to use. Okay? So in this case, we're going to use this top solution. Right? Because I said the intuition earlier was we need to store where waiter 1 is, where waiter 2 is, and which requests are left. Right? So that's exactly what we're going to do. So f of I, j, k is going to be, in words, the best possible, the shortest distance for the queries qk, qk plus 1, all the way through the end, qm, such that like with waiter 1 starting at table I and waiter 2 like starting at table j. Okay? Does that make sense? And our final answer that we're trying to compute is f of 1, 2, 1, right? Because waiter 1 starts at table 1 by definition. Waiter 2 starts at table 2. And we're trying to find the best distance for query 1 through the end. Right? That's the final answer that we're trying to calculate. So now, what's the recurrence here? Basically, at each step, we have a choice between sending waiter 1 to service qk or sending waiter 2 to service qk. Right? Let's say we send waiter 1 to send service qk. Then immediately, I'll pay a cost of the distance between where waiter 1 started and the table qk. Right? But then I'm going to recurse on the same problem with k plus 1 instead, k plus 1 onwards. But now waiter 1 is not going to start at I anymore. Waiter 1 is going to start at qk. And waiter 2 is still going to be at j. Right? So here's how the recursion is going to work. So it's going to be a minimum of two things. The first thing is d of like I comma qk. So this is just like the distance, let's say, between these two tables, plus f of qk j k plus 1. That's the first thing. Okay? Waiter 1, this is the case where waiter 1 goes to service the table. So waiter 1 is now at qk. Waiter 2 is still at j, and I'm looking at the remaining k plus 1 queries. Right? And I've paid this cost of the distance to move waiter 1 to that table. Second option is maybe I'll move waiter 2 to this table. So it's d of j qk, right? And then the second part would be f of, so waiter 1 is still at I, waiter 2 is now at qk, and I'm looking at the remaining k plus 1 queries, right? So the final answer is just the minimum of these two things. Okay, does that make sense? Any questions about this? Okay, and of course, you can see the runtime is indeed n squared m, right? Because this is the minimum of two things, so that takes constant time to compute, and there are n squared m states. And also, the space is O of n squared, because even though there are n squared m states, you'll notice that f of this k right here changes to k plus 1 each time, right? So we don't need to store the entire table. We just need to store like f of, like at a time, we just need to store f of something, comma k. And we can use that to compute like all of the f of something, something like k plus 1. Right? So we don't need to store everything. We just need to store a slice of the table of size n squared. OK? All right, so it looks like we have about 12 minutes left, and we have two problems. So let's go through them relatively quickly. So the first problem, number 17, is RSA. And this question basically says, if you gave me an algorithm that could solve 1% of all like encrypted messages through like encrypted using RSA, then I can give you an algorithm that will solve every message that encrypted through RSA. So remember, the setup for RSA is that we're going to start with some message M, and we're going to use RSA to give us some like encryption C. Okay? And the way we did that was we have some public key and some private. Here's our public key. Right? And what we're going to do is all we did was just say, OK, C is going to be equal to like you do what? It was M to the E, like mod N, right? And we're assuming that like our message M is like some string like in this like set. Okay, so and yeah, and then our C's are also, of course, because they're modding by N as well. It's going to be like some string here. Okay, so that's to set up the problem, right? RSA, M goes to E, M goes to C. Okay, and so now basically what happens is the problem says I give you an algorithm A. Okay, here's an algorithm A that it can decrypt 1% of all RSA like encrypted messages. Okay, what that means is that so we'll call N is really, really, really big. Okay, N is like this 1,000-digit number, right? So it's this. What this is saying is that A is able to decrypt 1% of all those numbers from 0 to like 10 to the 100th or something like that. Okay. What that means is like imagine like maybe there's maybe this situation where if the encryption you give me is divisible by 103, then I can somehow pull some magic and decrypt that message for you. But if it's not a multiple of 103, I can't do it. Okay, like that's the idea. It's like I have out of all the possible like messages I could get, like sorry, as the encryption, like 1% of them I somehow have a magic way to decrypt, but then the other 99% I don't know how to do. Okay, so that's the setup. I have an algorithm A which can decrypt 1% of the messages between 0 and n-1, but not the other 99%. And the question is, how can I use A as a way to solve to decrypt every message when it itself can only decrypt 1% of the messages? Okay. So part A is the setup, is like the motivation, is basically like show that RSA is multiplicative. That's pretty easy. So let's say I have message M1, which gives me C1, message M2, which gives me encryption C2. The goal is to show that the encryption of M1 times M2 is C1 times C2. And that is just by definition almost, right? We know how do we get from the message to the encryption? We do m to the e mod n. So if it is true that C1 is congruent to, well, I'll just use equal. If C1 is equal to m1 to the e mod n, and C2 is equal to m2 to the e mod n, then like by properties of mods, you can multiply, right? And so when you multiply them together, you get C1, C2 is equal to like m1, m2, all to the e mod n. Okay? That's just by definition of like how RSA works. So we'll see in a second why this is helpful. Okay. So now in part B, what we're actually asked to come up with this algorithm, right? So here's basically what's going to happen. So I have some message M and some encryption C. I have no idea what this message M is, right? But I know what C is. I'm seeing this encryption. And what I'm going to do is I'm going to choose a random M0 from like 0, 1, 2, n minus 1. Okay, random M0. Okay. And here's where the explanation gets a little bit more hand wavy. So basically, what I'm going to do is I'm going to take that message M0 and I'm going to compute its encryption C0. Okay. And basically the argument is that M0 was this like random number, perfectly random number between 0 and n-1, right? So raising it to the eth power and then modding by n, it's still going to be some random number between 0 and n-1, right? So that means this crypt right here, this encryption is just some random number between 0 and n, right? But I know like where it comes from, right? And now what I'm going to do is I'm going to multiply C0 with C. So I get C0 times C. And because C0 was some like totally random number, like in this set, C0 times C is also going to be some totally random number, right? Like if I give you a fixed number and I multiply by a completely random number, that gives me a completely random number, right? So that means that C0C is going to be some like completely uniformly random number between 0 and n-1. And now what I'm going to do is I'm going to apply my algorithm A to C0C, right? Well, that has a 1% success rate, right? Maybe C0C is this number, these special numbers that my algorithm A can decrypt. Maybe it's not. So what I'll do is I'll just keep on picking M0s, generating C0s, until I get a C0C where I can decrypt, right? And I know that there's a 1% chance. So if I do it a million times, like it's going to happen at least once that I can find something that I can decrypt. And then once I can decrypt it, I know that C0C decrypts to M0M, right? And then all I have to do is just divide out by M0, which I know, and that'll give me M. Okay? Does that make sense? So that's the intuition behind, that's a little hand wavy, but that's basically the idea behind this. Okay? All right, so let's do the last problem. So the last problem is this problem called edge connectivity. And so in the edge connectivity problem, the idea is that we have some undirected graph, and we want to remove from this graph the minimum number of edges possible in order to disconnect the graph. Okay? Disconnect the graph means separate the graph into two pieces that are not connected. So as an example, we gave you something like this. Here's a tree. Right? This is just like, here's a tree. Right? And for a tree, all it takes is removing one edge to disconnect the graph. Here's one section, disconnected. Right? For a cycle, it takes exactly two edges to disconnect the graph. I maybe remove this edge, now it's disconnected. Right. The question is, now I give you some arbitrary graph. What is the minimum number of edges I have to remove to disconnect the graph? Well, this problem is actually exactly something we've seen before. It's exactly the min-cut problem, right? The min-cut problem says, take your graph, split it into two sets of vertices such that the number of edges crossing the vertices is as small as possible, right? And that's exactly what we're doing. We're splitting the graph into two pieces by removing as few edges as possible. So we want as few edges to cross this cut as possible so then we remove those edges, right? But now the question is, if I just gave you a graph, just make it look a little nicer. How do you even go about finding this min-cut, right? So what's something about min-cut that we know already, like how to compute? We know from MaxFlow how to compute something called the ST min-cut. So it's technically the ST MaxFlow is equal to the XT min-cut. So what that means is that ST MaxFlow means what's the maximum amount of flow I can send from S to T, right? These two specific nodes, S and T. ST min-cut is exactly what's the best possible, what's the smallest weight cut that separates S and T from each other. Okay? So for example, maybe like S is this node and T is this node. So I have to pick a cut where like S and T are on opposite sides. Okay? And so that's called an ST min-cut. And recall that like ST MaxFlow gives you exactly XT min-cut, right? Well, we find a flow from S to T, and then in that residual graph, we can look at the edges, the nodes that are reachable with some flow left from the source, and that defines one side of the cut, right? And so, but that's always going to be a cut that separates S and T. And it's not going to be the global cut, right? The global cut may be something like this, where we separate this node and all the other nodes, but the max ST cut will only find cuts that separate S and T into two different parts, right? So how can we solve that? Like we want the global min cut, right? But we only have an algorithm for finding the ST min cut. So what's something very simple that we can do? Well, let's just run the ST min cut many, many times, right? So what I'll do is I'll just pick a node, any node, and I'll call that node S, okay? And then I'll just pick all the other nodes to try being T, okay? So maybe I'll pick this node as T. And now I'll use the ST MaxFlow algorithm to find the ST min cut of that graph. And then I'll say, okay, well, maybe I should try you as being T. Maybe this guy should be T. Maybe this guy should be T, etc. I'm going to try all the other nodes as this T. And so I'm going to eventually find the best cut between S and, like the best cut that, like, the global cut is going to put S in some set and the remaining in some set, right? So I'm just going to choose which of these nodes is going to be like in the, like picking this node to be T means that I'm going to separate S and T. Picking this node to be T means I'm going to separate these two nodes. And one of them is going to have to be the global min cut, right? Because one of them is going to be, like any cut is going to separate S and some other node. And so I'm going to check for what that some other node is for through all possibilities, okay? So what's the runtime of this algorithm? So the runtime is O of n times, so I'm doing this n times, right? One for each node. And then each time when I'm running a ST MaxFlow to find this, this min cut. So that takes O like times the runtime of MaxFlow, which let's say we're using Ford Fulkerson, so that's F star times E, right? E is at most n squared. And what's an upper bound for the flow, for the value of the flow in this graph? Remember, all edge capacities are 1. What's the upper bound for the value of the flow?
V.
It's n, right, exactly. It's V, or n. So that means the total runtime is bounded by O of n to the 4th. OK? All right. So yeah, that's it for the review session. So yeah, I'll still be here for a bit if you want to. If you have any questions about the problems that we didn't cover, the solutions will be posted once I'm on my computer again afterwards. Yeah. So good luck on the exam.